So today what we're going to do is we're going to study a thing called the probability model of the binomial distribution. Okay? Now, the way this comes about is it comes about from a possibility of having two choices. And we call those things a Bernoulli trial. So let me tell you what a Bernoulli trial is. So we have this thing called a Bernoulli trial, right? The Bernoulli trial, make sure you put trial here, is something where we have an event which can be a success. We'll call that P. And failure, we'll call that Q from now on, okay? So failure is a success. Success is what we're looking for, and failure is what we're not looking for. For this type of experiment or simulation, we consider anything a success to be what the heck we're looking for or what we want. So let me kind of give you the idea of how this works. So remember from last lesson, we were talking about trees. So our trees basically followed this kind of pattern, right? And then there was like a win, a loss, a win, a loss, and then another win and a loss. But instead of having different probabilities, there's always a probability of success and a probability of failure, right? Now, I could do this for, say, 3 levels, right? Now, you have all your 3 levels of winning and losses, right? So imagine that my probability to win was 3/4, right? Then I'd have 3/4 here and 3/4 here. But anywhere where I had a loss would be 1/4. So right here would be 1/4, right here would be 1/4, and so on. And you'd have your results, just like before. And so on and so forth, right? Now, let's go over what's happening here. If I was trying to find our probabilities, we'd have to go and figure out the probability of each of these by multiplying the edges to find each of the probabilities of, say, winning, 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 losses, loss, winning, winning, blah, 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 blah. We're not going to do that. I already made you do that in your exit task for the first lesson that we did today. So now I'm going to give you something that will calculate the wins that you're looking for. The wins and losses that we have here, actually, if we added up all of these, the probability of this would always be 1 or 100%. But you wouldn't believe this, but this actually follows a binomial distribution that we studied a while back. So this is how we calculate the possibility of winning and failing based on 2 possibilities. Now notice our problem will always be a thing that looks like a tree, i.e. a Bernoulli trial. You either have a win or a loss depending on which section you're in. And the wins and the losses never changes. The probabilities never change at all. So here is what we call this. This is the binomial distribution for probability. So we have the probability of X is given by the total number of things that you want and the subset, i.e. the number of times you actually want to win, is equal to, ready? Our wins, our P's to the X's, and then Q's to the N minus X. So we have a certain number of wins that we're looking for, and based on that, we have a certain number of success failures. So how do we use something like this? So we're going to use this beautiful calculation thing here to do a lot of work for us. Instead of drawing up a big tree and figuring out the probabilities, we're going to use this thing to cut down on the work that we have to do because, you know, we don't have time anymore. So here it is. So imagine that you are in a company, right? And if 0.1% of the products are defective, if a client has 25 products, what's the probability that at least one is defective? Okay, now remember what our equation is. P of x is equal to n choose x, p to the x, q to the n minus x. Okay, so now here's what we want. Let's press write down the idea of winning. We want to find something. The winning part is a defective product. So in this case, our p-value is 0.1%, but we have to change that into a decimal. So our answer for p is 0.0001. And that means our q value is just the opposite, 1 minus q, which is 0.999. So that is our q and that is our p. So the key idea is, one, you always kind of have to define what your winning means. And that's our defective product. Okay? Now, they also told us what n was. They said, too, n was equal to 25 products. Now, what we are looking for at least one. Okay? Now, we can save time by either doing this, finding one product, finding the probability of one product with this thing, and then 2 products with this thing, and then 3 products, and then 4, all the way up to 25. Or we can do something crazy. We can do the opposite of that, i.e., we can take 1 minus the probability of none being there to get the total. Okay, so we're going to use the indirect method. And so what we are looking for is at least 1. So let me show you how I would write that in mathematics lingo. We would write this: P of x being greater than or equal to 1 would equal to just P of 1 plus P of 2 plus, and it would go on forever, wouldn't it? And we don't want to do that. P of 25. We don't want to do that, but we can use the complement, i.e., we know that 1 minus P of 0 will give us our answer. So we're going to use our basic equation there. So we got 1 minus, well, 25, choose 0, times 0.01 raised to the 1, times 0.99 raised to the, well, there's 25 trials. If I have 1, that means there's 24 failures, right? Punch that in your calculator and you get the following answer. So 1 minus 0.975, which gives us our final answer of P of x being greater than or equal to 1 being this, 0.025. Therefore, the probability of finding at least one is 0.025, or otherwise known as 2.5%. And we're done. All right, so a game consists of rolling a pair of dice 10 times. Each sum that equals either 6, 7, or 8, you're going to win $1. And then what is the probability of winning? 6 out of 10 times. Is this a fair game? And fairness is equal to NP. So remember, you're using $5 and you're running a certain number of times and you're doing all these calculations. So let's go through and do the math. Now, in order to solve this, right, we got to start thinking about rolling our dice again. So we got to kind of identify on our die how we can get a 7, a 6, and 8. Okay, so let's see. 6 has, so the total number of spots is so the probability of 6, 7, and 8 is that. And so that means our P in our original equation, remember, P of x is equal to the following. N choose x, P to the x, Q to the n minus x. So we've got 4/9 is our probability, right? Now that we have that, our Q value is the complement. So Q is equal to 5/9. So now we know from before that the total number of rolls that we have is 10. But our X value, our winning, remember our X value is the number of wins, is going to be 6. All right, so let's calculate that. So P of 6 is equal to 10 choose 6. And then we're going to have 4/9 raised to the 6, and then 5/9 raised to the 4. Punch that into your calculator and you get this final answer, which gives us this final answer of 0.15. P of 6 is 0.15, which is really just 15% chance. So to get 6 possible wins, it's a 15% chance. So now let's go and figure out if this game is fair. So I'm going to introduce you to the concept of fairness in a game. Okay, so the concept of fairness. And that is, fairness in any game is if I put $5 in, will I get $5 back in the end? Okay, that is your question. So a fairness in a game means you always break even. And for a thing called, for this binomial distribution, which is no more than just the general term of the expansion that we had, it's given by, for the binomial distribution, we have this P of X is equal to N choose X, P to the X, Q to the N minus X. So it's always by wins and losses. And remember, these are the number of wins and these are the number of losses. Now, when we are doing this for the binomial distribution, its fairness, the way to calculate its fairness is to take all of the probabilities of winning and multiplying by the number of trials. So for fairness, for this type of experiment calculation, you have to take n is the number of times that you're playing and multiply by its probability of winning. And if this equals the money that we put in, the game is fair. So now let's go back to our problem. So for B that we had, right, n was equal to 10 possible games that we were going to play, right? The probability was 4/9, wasn't it? Okay, so let's go and calculate that. So that means our fairness calculation is going to be just, remember, it's NP here. So we're going to take N, which is 10, times 4/9, and you end up with 4.44. Oh my goodness. Is this fair? Now, let's see, is it? And so this is why I don't go and gamble, because most of the calculations that are in there on all of the games are based on fairness, and the house is designed to always win. And that's why when you go to a lottery or you go to the casino, you're always going to win. You're always going to lose. But every once in a while you win, and you win big, and that's when you get out. So now what I'd like you to do is to do the problems that are on the website, and then we'll start preparing for our test.